Cool. Yeah, cool. So, yeah, thanks, um, everyone for joining this talk. So yeah, I'm gonna talk about world models. I guess this is one of the recent buzzwords in AI. Um, so hopefully, through this talk, you can get some high-level ideas of world models. I'm not gonna dive into a lot of technical details, but instead trying to give you a big picture of this topic. Okay. Um, yeah, so yeah, by the way, feel free to interrupt me if you have any questions during the talk. Okay. Um, yeah, so these days we have seen a lot of success in like large language models and large vision models, right? Like with large language models, right, you can ask whatever questions, right? And it will somehow give you an answer, right? And recently, right, people built these large vision models, like video generation models, right, that can simulate or generate videos that is kind of very realistic, right? You cannot even distinguish whether it's the real video or it's kind of generated by the model, right? Yeah, let's watch one more. Okay. There are a lot of kind of these fun videos you can search online. So yeah, with this video model, you can actually create a lot of things. Okay. And also the recent so-called reasoning models, right? Like DeepSeek R1, OpenAI, right? There's kind of they have like O1, O2, O3, right, and O4, right? All these different versions. They can do, for example, math reasoning, right? They can solve mathematical questions very well, right? Here, this benchmark, right? AIME. This is the a set of math Olympic kind of context questions, right? So somehow this model can solve this type of very difficult mathematical questions even better than humans, right? So with all these kind of progresses, right, people have been making in the past couple years, right? There are also kind of debates and noises about the so-called AGI, right, artificial general intelligence, or even ASI, right, artificial super intelligence. Okay. Say OpenAI, right, they claim, right, so we're gonna achieve AGI very soon, right, and they even lay out different stages of achieving AGI, right. First level is the chatbot, right? It's something they have achieved with ChatGPT, right? Maybe roughly 3 years ago, right? Like this chatbot can kind of do whatever kind of natural conversation with humans, right? And level two, they claim is the reasoners, right? To do human level problem solving. Those results we have seen, right? Using the reasoning models to solve mathematical questions, right? They is kind of part of this level. Level three, agents, right? This is perhaps the stage we are now, as claimed by OpenAI, right? People are building agents, AI agents, right? These days, right? And right after this talk, we have the next lecture, right, about agentic AI. So agents are the systems that can take actions and solve complex tasks. Okay. Level four, the claim is the innovators that can aid in inventions or like scientific discoveries. Okay. Level five is the organizations that can, AI can do the work of an organization, right? So it's not just a single agent. You can see it's a bunch of agents that organize together, collaborate with each other to solve even more complex problems, right? But at the same time, right, there are kind of other people, right? They have different opinions. They believe that large language models or these kind of large vision models, right, they are still not yet at a human level intelligence or even like a dog level intelligence, right? They believe that some fundamental capabilities are still missing, right? Like understanding the physical world, persistent memory, reasoning and planning, right? And some people said the intelligence, we have achieved is more like a, jagged intelligence. Okay. Sometimes the machines, they can solve very complex problems, right? As we've seen, like Olympic kind of mathematical questions, right? That humans cannot even solve, right? Those models can solve pretty well. But at the same time, these models, they may struggle with very simple dumb problems, right? This is, for example, this is a pretty well-known example. A couple months ago, right? Most of the models at that point, they cannot really answer this question well, right? Which number is bigger, right? Most of the time, the frontier models, they pick the wrong answer, right? So that's kind of the current status quo of, these large language models, right? Or the latest frontier large models. Okay. So, right, we want to ask, right, do current large models really understand the world, right? I'm going to show you a couple of examples so that you can have a better sense on the capabilities or limitations of the current large models. Okay. Here's an example. We built this world model, we call it world model atomic benchmark, where we measure the atomic capabilities of the models, across different dimensions. The first set of dimensions is about perceiving the world, like how well the model can understand space, for example, and the time, right, and quantity, and the visual processing, motion processing, right. And then the second set of dimensions includes this prediction of the world, right? Can the model predict the next step of the world, right? From the psychology perspective, that's the mechanistic knowledge. And can they compose this capability into multiple steps, right? That's the transitive inference. Or can they compose in this way, right? That's compositional inference. Okay. So here are a couple examples. Right, we ask this very simple question, right? Are the two trajectories the same, right? Obviously, right, they are not the same, right? The circle and the triangle, right? But the state-of-art models like O3, right, the so-called reasoning models, right, they cannot really answer this question correctly, right? If we measure this in on a larger set, right, this is a very simple question. Surprisingly, all these frontier models, they cannot perform at the random guess level. Okay, roughly 50% of accuracy. Right. Here's another example about the spatial understanding. Okay, is the purple object bigger than the red one? Okay. Again, it's kind of the reasoning model, they achieve roughly 50% of accuracy. Okay, and interestingly, if you ask the question in a different way, right, is the left object bigger than the right one? The accuracy is even lower, right? So let's show some systematic bias inside these models, right? They cannot they do not really understand left or right, right? Or maybe there's kind of some bias here, right, leading to this lower than 50% kind of accuracy. Right. Okay, so here's some more systematic results, right? We measure all these dimensions, right? And for humans, right, we can achieve roughly 90% or 100% accuracy, right, across all these dimensions. But if we measure all these frontier models, right, their performance is roughly, for some of the dimensions, right here, the spatial understanding, right, some models only achieve roughly 50%. Again, that's a random guess. And particularly for some of the dimension like compositionality, transitivity, right, you can see all the frontier models, right, they still have a large gap from human level performance, right? Okay. So the next example, again, is a very simple example. Okay, the task is about moving the blocks to the goal state, right? So you are given this initial state of the blocks. I want to generate a sequence of actions to move the blocks so that I achieve the goal state. With large language models, right, we all know, right, this model, they do autoregressive generation, right? They generate a plan token by token, right? And like GPT-4o, somehow they can give you a plan which looks pretty good. But if you actually execute this plan, you will know some of the steps, they are actually not valid, right? Like here, the yellow block is still under the red block, so you cannot really pick up the yellow block, right? In comparison, right, to how we humans solve this type of problem usually, right? We humans do this strategic planning, okay? We have an internal world model to predict the states, and then we simulate different alternative plans, right? For example, right, given these initial states, we're gonna simulate in our minds, right? If I pick up orange, what's gonna be the next state? And then if I continue to stack this orange on blue, what would I get, right? So we're gonna imagine or simulate these different consequences of actions, and then we're gonna simulate different alternative plans, right? If I instead pick up a blue, what would happen, right? And with all these different alternatives, we're gonna assess the outcomes and compare, right, which path is more promising, right? And then I'm gonna pick the best. Like say this one is more promising, right? So I'm gonna continue this simulation through this line, right? Until I find the solution. So you can see, right, side by side, the reasoning behavior is very different between humans and the large language models. Okay. And somehow this, again, the reasoning models we mentioned, right? Some of the reasoning models, they try to emulate this form of reasoning, just like humans reasoning, right? For example, DeepSeek R1, right? Here's an example. We prompt the model to select a random number, okay, for a simple question. And the model is gonna generate something like this, right? Okay, the user wants me to think of a number between 10,000, blah, blah. Let me see, well, humans often have favorite numbers or patterns, maybe go with something like a 7777, but there's 4 sevens, which might be too obvious. Alternatively, 1, 2, 3, 4, blah, blah, right? And the weight, blah, blah. So it's kind of trying to simulate this behavior, right? With backtracking, validating, self-validating the answers and the rethinking about the reasoning, right? Repeatedly, right? But obviously, with the from this example, you can see, right? It's kind of emulating this behavior in a kind of unnecessary way, right? Even for these very simple questions, they cannot really understand, right? How what type of how complex this reasoning could be, right? So so here's the third example, okay? In a social reasoning context, okay? In social reasoning, the first thing, right, to be able to do social reasoning is to understand humans, right? So that's with understanding of humans, you can do, right, how you can collaborate with humans. So here's again a very simple question for human, right? Given this image, right, we ask, is this person on the right helping? Right? Is he helping? He's helping. Okay. Yeah. So we ask ChatGPT. It says the person on the right appears to be helping by holding the chair, probably to steady it or to move it into place. Blah blah, right? It gives you a very kind of lengthy evidences and supports to support his claim. But so from this we can see, right? So the model it somehow can understand the action, right? It says correctly, right? The person is holding the chair, right? But it does not really understand the intent, right? Is this the person is not really helping, like he's doing a prank on a woman, right? So understanding humans is not just about understanding the actions, right? You observe the actions from the pixels you see directly, right? But there are kind of hidden variables behind the actions you observe, right? Given the actions, we humans, have the capability of so-called theory of mind, right? That's the capability of reasoning about hidden mental variables that drive the observable actions, right? For example, right, we perform an action because we have a goal, right? We want to achieve some goal, and we have the belief about the world, right? Based on this, we know, okay, this is the action I should take, right, to achieve my goal. So we observe, similarly, right, we observe others performing different actions. We have the ability, right, to infer what that guy is trying to achieve, for example, right? So that's the kind of understanding of other agents, right? But yeah, these models, obviously, they have very limited capabilities in terms of theory of mind capability. Right? So quick summary, so far, with these couple examples, we can see, right, these frontier large models, they fail surprisingly easily, right? And somehow they kind of lack consistent understanding of reasoning of the world. And in comparison, right, humans have an internal world model for consistent reasoning. Okay. This idea of world model is from psychology and cognitive science, neuroscience. Right? If you're interested in this topic from this field, you can check out this couple papers, like how we reason or hypothetical thinking. Okay. So next, I'm gonna dive a little bit deeper into this concept of world models and talk about how in AI we formulate world models and how we use world models to improve machine reasoning. Okay. So what is a world model? Right. So yeah, world model in humans, again, this is a very classical topic, right? People in psychology have studied this for many years, right? We humans use world model to understand the world. Like say by watching this video, we can understand, right, the property of the box, right? The material is pretty bouncy, for example, right? And then we based on the understanding of the world, we use the world model to predict the world. Right? By watching this instance, we can predict, right, in the next instance, how this fluid liquid would drop, right? And how this liquid will be divided into the left and the right beams, right? We have the capability to predict the dynamics. And with this ability to predict, we can do this control and planning, right? So we know, right, how we should tilt the angle of the the glass at the right angle to avoid the spilling of the liquids, right? And this capability already exists in very young child, right? And also, like, we humans can learn to use tools very quickly, right? Use with just a few trials. Right. Here's a very simple example, right? Like say in this configuration, right, we want to get the red ball into the green goal. So how human is gonna do this, right? We're gonna try a couple times first to understand the world, right, the configuration. Okay, this does not succeed, so I'm gonna try again. So after this, I kind of figure out, right, how this particular world works, right, in this problem. So in the third time, I'm gonna be able to solve it, right? So the key underlying this is that we humans use a world model, right, to simulate the outcomes of possible plans, as we mentioned earlier, right? In our brains, right, we're gonna sample all different possible actions, and we simulate the consequences of different actions, right? And then at some time, I'm gonna choose a particular action. I think is the optimal at this point, right? So I'm gonna execute the action in the real world to see whether it succeeds or not, right? And then observe the outcome. I get the feedback. I'm gonna use this feedback to update my world model, right? Update my understanding of the world, right? And then I continue to simulate, right, with the new world model, right? With this, with a couple iterations, I can solve this problem very quickly. Right. Okay, so let's handle world models in human, right? The intuitive understanding of world models. And the world models in AI, okay, this term is also not particularly new in AI, right? People have been formulating world models, this idea in some of the fields in AI, like especially reinforcement learning and robotics, right? We call it model-based planning or model-based reinforcement learning. Okay. So mathematically, in AI, we formulate world model as a state transition probabilities, or we can call it the next word prediction, right? We know, right? Large language model is doing next token prediction or next word prediction, right? Generating the next word. Here, you can intuitively think of world model as a predicting the next world, okay? Or next state of the world. So given the current state of the world, given an action, the world model predict what's gonna be the next state, right? Or you can see it as predicting the consequence of the action, right, on the current state. So that's the basic formulation of world model in AI. And once we have this ability of prediction, as we mentioned, right, you can do reasoning and planning, right? So the paradigm, somehow we call it the simulative reasoning, okay, is like this, okay? Given the current state, say you have a goal state you want to achieve, right? So what usually we're gonna do, right? We're gonna simulate different plans with world model, right? Given the current state, if I take action 1, maybe I'm gonna achieve here, right, the next state. If I continue to take action 2, right, I'm gonna achieve here, for example, right? So you can simulate a sequence of actions and the corresponding state, right, until you arrive at some point and you realize this is not the right plan, right? So you're gonna continue to simulate another plan until you find the right plan, right? So after simulating plans with world models, you're gonna choose the best plan, right? That's how we do reasoning, okay? We call it the paradigm of simulative reasoning, right? Because you are using world model to simulate, and then you choose the best, okay? So within this paradigm, a special case, which is very well known, is the AlphaGo, right? You can see, right, AlphaGo, how it beat humans, right, in playing Go, right? It's basically trying to simulate all possibilities of playing the Go, right? Given the current state of the board, right? It's gonna simulate, okay, if I put this piece here and I continue to play until the end, do I win or not, right? So with the power of computing, right, it can basically simulate many possibilities, right? And then it finds the possibility that give you highest probability of winning the game, right? So in this case, the world model here is very trivial, right? It's known because given the state of the board, right, the action is basically putting a piece on the board. Then you know exactly, right, what's the next state. There is no uncertainty at all, right? So in this case, the world model is trivial, right? It's deterministic, right? Is a kind of a known world model, right? but in practice, when solving other problems, like say we want to have an AI that can drive a car automatically, right? In this case, the world model is not deterministic, right? And it's not known, right? Say if I turn left, what am I gonna see, right? So you have to build the world model, right? You have to train a world model that can predict, okay, on the streets what's gonna happen, right? So that makes the reasoning problem way more difficult than playing a Go, right? So prior research, in this field, right? They also they try to build these world models, right, to solve different problems that are more difficult than Go, right? Primarily in robotics and embodied AI, okay. The prior research usually they build domain-specific world models, right? Given a problem, they build a world model specifically for that problem, right? So they build the physical engines or embodied simulators, right? Like say for this particular robot, right? They're gonna build a model for this robot, right? And for each action the robot can take, right? The simulator can simulate what will be the next state of the robot and the environment, right? So you can see this as a world model specifically for this robot and the environment. And similarly here, right, is a slightly more complex world model for the indoor robots that is doing kind of like household tasks, right? So again, it can simulate, for example, if a robot move forward by one step, what's gonna happen, right, in the environment. Okay. So you can see this as a kind of a rule-based or physics-based simulators, right? Humans, they write all the rules, right, in the engine so that it can simulate the consequences. Okay. Here's another set of fixed engines based on some neural models, right? They somehow use a neural model to model the dynamics of each of the objects or each of the particles. So they can simulate, right? What's the next state if I apply some force on the object, for example, right? So again, these are all very specific to a particular domain. The third category is kind of video prediction models. Right, this was a very classical work in AI, that build world models for playing this particular game, right? That can drive automatically, right, in the environment. Okay, so again, right, so the model is basically doing this, right? Given the state of the game, right? If I move forward, what's gonna happen, right, in the game? Okay. So this is represented as a video generation model. And this was work in 2018, and 6 years later, people have been able to build this video prediction model. Here, all the videos was generated by a model, the world model for auto driving, right? So again, right, the model can simulate if I turn left, what's gonna happen, right, on the street, pretty realistically. Okay. But anyway, these models you can see, right, they are trained specifically for auto driving, right? And even further, say this particular model, it was trained specifically for driving in London. Okay, you can see, right, all the vehicles they drive on the left, right? So this model cannot be applied to like for driving in California, for example, right? Because the traffic rules are different. Okay, so these are domain-specific world models, right? And once we have this world model, right, you can see, right, you can predict, right, the street states in London, right, after taking action, you basically solve the problem of the driving, right, because you can do this simulative reasoning, right, to know what's the best action I should do at this point, right? So with this, right, we can see, right, the scope of simulation basically defines the capability of reasoning, okay? or we can say the more simulation, the more intelligence. Okay. If you can simulate the state of streets, you know how to drive automatically. Right? If you can simulate, yeah, right here, right, for all the driving, right? If you can simulate what would happen on the street if I turn the vehicle left, for example, right, or doing other actions, you solve the auto driving problem, right? If we think it's slightly in a broader way, right? If we can simulate what biological effects would arise from, for example, a specific genetic mutation, right? Or if we can simulate what the biological effect would arise from by applying a specific drug, then you basically solve the problem of drug discovery, right? You could try to optimize over the drug, right, to find the optimal drug that can achieve the right biological effect you want to achieve, right? So, in some sense, right, for this particular world model, you can see the nature has been doing this type of simulative reasoning with this particular world model for 4 billion years, right, to create a life, right? So, right, the nature, they generate mutations with these molecular genetic mechanisms, right? Here, the world model basically is to generate the phenotype given the genotype, right? The action is basically a genetic mutation, right? And once after it simulates all these different possibilities, it's gonna choose the best options that fits our environment, right? And then it repeats this process for many years until it arrives at this kind of state, right? With very diverse intricate forms of life, right? So somehow, from this simulative reasoning perspective, the nature, right, is doing this type of reasoning, right, to create the right form of lives on Earth, right? Right. So and for other domains, the same, right? Say to solve the mathematical reasoning, right? We can simulate, right, the consequence of different mathematical operations, right? We can again like search for different derivations and then find the best one to solve a particular problem, right? And in business, right, we can simulate, say, how might a business grow if a specific policy were applied. Then we can find the optimal policy, right? So that's basically the power of simulative reasoning with world models, right? And if we try to organize this kind of simulation and the respective intelligence based on the scope of reasoning, we can somehow have this kind of diagram, right? Somehow we put language simulation as the basic level of simulation, okay? Like math coding, right? The logical reasoning, you can see they can be represented as a symbolic language, right? Right. So once you can simulate this type of symbolic language, right, you can solve math and coding. And we have a world model that can simulate space and time, right? We can have this like physical reasoning, including auto driving, robots, right? We can simulate this multi-agency, right? Or even the agent, how they interact with each other, what will be the consequence, right? You can do this kind of social or business reasoning, right? And one of the ultimate goals of AI, right? We want to do this scientific discovery or understanding of the universe, right? So if we can simulate this, how the universe works, right? As we mentioned, right? The effect of a genetic mutation, for example, right? We can do this, like say drug discovery, for example, right? So this kind of diagram somehow give you a chart, right, or roadmap, right, how we can achieve, more general intelligence, right, step by step, right. Somehow you can see there's some, uh, similarity with that, 5 stages laid out by OpenAI, right? With language, you can do chatbots, right? With space and time, you can build the physical agents, including robots. Right? Multi-agency is kind of an organization, right? Or the business. With a law of nature, right? You can build a scientist, AI scientist, or like inventors, right? Okay, so yeah, let's kind of kind of a big picture of the water models and the scope. Before moving on, I want to pause here for a little bit to see if we have any questions so far. Yeah. Yeah. Yeah, exactly. So it's a probabilistic model, right? So given the action of my vehicle, you have to predict what other agents are gonna do, right? So you will be able need to simulate all different possible futures, right? So a right world model should give you the right probabilities of different possible futures, right? And based on that, uh, you can have an expectation, right? What action is the best action, in expectation, right? So yeah, there's uncertainty, and yeah, it's a probabilistic model. Yeah.
Which is just in your like circles. I guess that would, so in order to do this, you're saying if we could simulate, then we would do that. But in order to be able to simulate, then you would.
Yeah, that's a very nice question. So, basically, as we mentioned here, right, whatever you can simulate, basically what type of intelligence you get. But the question is, right, is the difficulty or complexity of simulation, the same as the difficulty or complexity of doing this type of reasoning or understanding itself, right? So yeah, that's indeed a very good question. So the point here is that, as we'll see later, building the world model itself give you kind of advantages from the computing perspective, right? So the idea here is that the world model, it kind of model this particular step, one single step in this whole process. So you can use a lot of data, right, to train this particular function. And the reasoning is basically about composing these steps, this one step, right, for many, many times. And you achieve this complexity of reasoning, right? So here, the this is a good example here, right? So the world model only need to model this one single step, right? If with one single genetic mutation, what will be the consequence of this particular mutation, right? And then you apply this function for many, many times, you can arrive at this, vast diversity of lives, right? So the nature, it does not really define what's the ultimate form of lives, right? It only defines this single step, right? This basic principle here, right? And then the complexity will emerge from this single function, right? So you can see somehow the large language models, they are kind of also applying this kind of idea, right? All these language understanding tasks, right? They actually have a single uniform formulation, which is next token prediction. As long as you can predict the next words, given the previous words, right? People show that, okay, you can build a large language model that can do all these different type of language-based reasoning, right? So that's one of the kind of the key things we learn from building large language models, right? Because before large language models, people thought, okay, to understand natural language, right, we have to formulate all these different tasks, okay? How to do conversation, how to do question answering, how to extract named entities from a piece of text, right? So you can see in classical natural language processing, there are kind of hundreds of different tasks, right? But with large language model, people found, okay, you can formulate all these tasks with this single function, next token prediction, and then solve everything. Right? So the same here, right? With world model, once you can predict next state, you can arrive at very complex reasoning capabilities. Yeah. Mm-hmm. Yeah, so that's a very nice philosophical question, right? What's the purpose of the universe, right? I don't know. And what's the purpose of life, for example, right? So I'm an AI researcher, not yet, philosophical researcher. But somehow, maybe, right, there are somehow some basic rules at the very beginning of the universe, right? You can see in physics, people are building this standard model or a theory of everything, right? There are 4 basic forces, right? Strong force, weak force, gravity, and electromagnetic forces, right? And with these, fundamental things, again, the universe just evolve, right? By applying these basic rules, for many iterations, and you see all these different very complexity in the universe, right? But is the universe optimizing for anything? I don't know. Maybe it's trying to maximize the entropy, right? So, yeah. But anyway, any other questions? Okay, great. Yeah. So now we have seen, right, this paradigm of world models and simulative reasoning. Next, I'm gonna show you some instances, right, how we use world models to really solve some concrete problems, and how we build better world models, right? Again, following this particular roadmap. Okay. The first, let's see, right? If we can simulate language, what thing we can achieve, right? So we all know, right? Large language model, they can simulate natural language pretty well, right? So let's use language model itself as a world model. Okay. So for example, right, we have seen this, right? To solve this block moving kind of task, right? Humans, they do this type of simulative reasoning, right? We can try to be inspired from this simulative reasoning, right? And use language model to simulate this process. Okay. Here, we using language model as a word model basically means you have to describe everything with natural language, right? So here again, basically you need to have this function, right? If you can describe the state with text and the action as text, then we can use a language model to implement this function, right? Basically the word model. So in this case, right? Say for this state, we can describe with natural language, right? Orange and blue blocks on the table, red block on the yellow block, right? And then given this pickup orange, this particular action, right? We can use language model to generate the description of the next state, right? Orange in the hands, blue block on the table, right? Blah blah. And then once we have this function, right, implemented as as a language model, right, we can do this simulative reasoning, right? And this pretty much the same as the AlphaGo type of reasoning, right? We're gonna build simulate different possible plans, right? First, given this kind of simulation, we're gonna select which path here now is the most promising. And then I'm gonna simulate the next possible actions. I'm gonna continue the simulation until I arrive at the final state. Okay, and then I have a reward, right? Do I achieve the final state, the targeted state, or how different is the final state, from the targeted state, right? So I have a reward. I'm gonna backpocket the rewards all the way back to update the value of each of the intermediate states, so that in the next iteration, I can repeat this process, right? Which one is the most promising so far, right? That's basically the Monte Carlo tree search, right? MCTS type of planning algorithm. Okay. So with this, we have this results. With this simulative reasoning, by using language model as a world model, we achieve like a 50% success rates, on problems of different difficulties. And here, other numbers, these methods are like chain of thoughts. This is basically the method we mentioned at the very beginning, right? Using language model to do token by token, word by word plan generation, right? And we can see, right, with this, by treating language model as a word model and doing this simulative reasoning, we have major improvements over this token by token plan generation. Right? We can do math similarly. Okay, so this is a math question, right? Judy is reading a book. She read 12 pages yesterday, blah, blah, and how many pages should she read today, right? We can do solve this problem in a similar way, right? Here, we can define the state as the intermediate values of different variables, okay? And the action is a sub-question for an unknown variable, okay? So you can see the reasoning process, right? At the very beginning, you know nothing about the intermediate variables, right? So you first have a question, an action, like how many pages did Julie read today, right? So you have this intermediate state, right? A value of particular intermediate variable. You continue to and ask different sub questions, right? Until the state contains the answer to your final question, right? So that's how you could decompose the mathematical reasoning into this state and action kind of planning type of question. Okay. And again, right, with this, you can have way better performance than, this traditional token by token kind of reasoning method with language models. Yeah, so let's have a simple example. Okay, using large language models to play as the role of a world model to solve some mathematical and coding and logical reasoning problems. Okay. Next, okay, say now I want to go beyond just language reasoning, right? I want to build like auto-driving vehicles and robots, right? So we need to simulate space and time, right? Right. So for this type of problems, right? Again, right, we believe, right, language is not enough, right? We need to model other modalities like videos, or audios, or other sensory informations, right? So because language is often not the most efficient medium to describe all information during reasoning, right? For example, right, in auto driving, right, we need to describe the street state, right? We need to model the state of the street. It will be very difficult to use a text, right, to describe all the vehicles' locations and movements, for example, right? And here, say you want to pour liquid into a glass without spilling, right? It's basically impossible to use natural language to model, to describe the viscosity or volume of the fluid, the shape and position of the container, right? So natural language is not the best modality to describe this information, right? We need other modalities like videos, for example, right? So, right, then to build this type of world model, right, for physical reasoning, right, we need to integrate these different modalities, text and video. And here's a particular example, right? We can say we can model a state as a video and use text to describe the action. Okay. And we can build a world model to basically for this particular function, right? Here's a particular instance we are working on. So this is the model we're building. There's a particular backbone that can predict the next state of the world, and we kind of decode the state into videos, right? With a video diffusion decoder. I believe you all have learned this in the past couple of days, right? In the diffusion model. So here you input action, and then the model is gonna predict the next state as a video. You can continue to input the next action given the current state, and then predict yet the next state, right? In a sequential way. Here's an example, right? Say given this current state, right? You're controlling the robot, right? Two robotic arms. Say you input action, brush the baking pan. The model is gonna simulate the consequence of this action, basically, this video, right? And then I give the next action, add the seasoning. You're gonna pick up the bottle and then add the seasoning. We continue, like say, open the oven. Right. So in this model, right, we use language to describe the actions and then use videos to describe the state. Okay. Right. And in comparison, right, with this model, right, this world model is very different from the standard video generation models maybe you have seen, right, in the past couple days, like Sora, View 3 or Cosmos, right? From the model architecture perspective, you can see, right, a standard video generation model is basically this type of model, right? You give a text prompt into the model, into a diffusion model, the model will give you a piece of video. That's it, right? But for world model, you need to do this kind of interaction, right? You need to be able to input the actions one by one, and then with each action, you need to predict the next state, right? So these are different type of capabilities, right? So you need to support this real-time interaction, right? And because you need to simulate, states, right? With this kind of sequence of actions, right? You need to make sure there's a kind of long-term consistency, right, between the different states, right? So with this model, you can simulate, for now, you can simulate up to 10 minutes of this kind of videos. In comparison, usually the state-of-art model like View 3, they can simulate maybe 10 seconds of videos, right? And here we use massive video and text data to train the model, starting from a large language model as an initialization. I'm gonna skip the details. I'm happy to discuss more offline if you have more interest in this. Okay. So anyway, there are kind of more results from the model, right? So just we have seen, right, in the Gaia model, right, they can simulate even the possibility of the state of the streets, right? The same here, for robots, you can simulate even the possibilities of a given action or given different actions, right? Right, and again, as a reminder, right, once you can simulate the next state, you can do this robotic simulative reasoning, right? Like say, if I make this action, this is the state I'm gonna achieve. If I do this action, this is the state I'm gonna achieve. So you try to simulate all different futures, and then you'll find, right, which future is the future you want, right? So you'll know, okay, I should take this sequence of actions, right? Okay, that's the manipulation of robots. Here's another set of another example. We call it the locomotion of robots doing this, causal grains kind of actions. So here we input actions one by one, right? Wave hand, on and jump, dance, 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 grab the rope behind and show to audience, right? So the model can again simulate the state given the actions. Make a heart shape with hands, right? So the model is trained with a lot of video data, and including this robotic video data. So with these different input actions, it can simulate pretty realistically. We can also simulate driving, especially these kind of very dangerous situations. You can see, say you move forward, and suddenly there's a pedestrian in the middle, right? So the model can try to simulate different scenarios, including these very dangerous situations. So somehow this is a way to guarantee security safety, right? In all driving, you have to try to anticipate all possible dangerous situations, so you know okay how to avoid that. Okay, it's an example of some kind of fantasy type of game type of situations. Okay. Okay, so those are the example from the Pan World model, which is a pretty general domain general model that can simulate different scenarios, driving, robots, and other environments. Okay. Yeah. Any questions so far? Yeah. Yeah. So basically, how you apply world model in reality, right, for reasoning? Exactly. So that's a very nice question. So the world model itself, as I showed at the very beginning, right, how humans learn to use tools, right? That's an example. Basically, so given the current state, you want to decide what's the next action, right? So you're gonna use a world model to simulate, and then you choose this action. You believe based on the current world model, this is the best action I should do. Then you're gonna really execute this action in the real world, and then you really observe the real consequence in the real world. And then you're gonna use this as a supervision to update the world model, right? So yeah, in practice, you can update this world model in real time, right? You collect, you execute actions, you get consequences, you update the world model in real time, and then you continue to use the world model to decide what's the next action, right? That's the ideal pipeline. Of course, now we haven't yet achieve this, right? The world model itself is very big, very complex. The simulation is very slow, so we haven't yet arrived at this status like you can deploy world model in real time, right? To get real time feedback and updates, right? But we are on path towards that. Okay. So with world models, right? We have been talking about that, right? We can do this simulative reasoning, right? I want to mention briefly another usage of world model, right? You do not really use world model, on the fly, right, to decide the next action. Instead, you can use world model to train the reasoning model, right? So let's once you train the reasoning model, like you say whatever, like a large language model, right? Use a world model to train it. And then the model hopefully we hope the language model can learn better reasoning, right? So this is a kind of another type of usage of world model. Let's see an example, right? Say for now, we see right, large language model and vision models. They were trained mainly with large scale text data or vision data, right? But they do not really learn by interacting with the real world, right? They lack this real world experience, right? So I've seen at the very beginning, right? These models they cannot really understand real world physics, or understand other agent behaviors, right? For example, right? Again, using human learning as an example, right? How we humans learn to like do this log climb, right? We do not learn this just by reading books or watching like tutorials, videos, right? Instead, we have to also practice in the real world, right? So that we get real world feedbacks, and we learn this skill in a better way, right? So the same, right? For large language models and these agent models, right? We hope that this model can also learn not only from just text corpus, right? We want to deploy the world model, the language models or agent models in the real world and get feedbacks, right? Right. We need to learn by interacting with the world. So the traditional way to do this is okay. I just deploy the reasoning agent actually in the real world, and then I do actions, I get feedback, and I train the reasoning agent, right? But this one usually is very difficult. It's very expensive and very slow to get feedback, right? Say you want to really learn, train all the driving model, right? You can. It's very dangerous and very expensive to really, deploy the vehicle on the real street and just let it drive, right? That's kind of not practical, right? And this is literally how actually some of the companies they are doing, right? They actually deploy, say this is the Tesla, right? They deploy the robots, right? A lot of robots in a real physical environment, and then let them do the tasks, so that you collect feedbacks and train the robots, right? And because the robots they are so crappy right now, they cannot really do these tasks very well and get meaningful feedbacks. They have to hire a human to teleoperating these robots, right? And then so that they can get better feedbacks, right? So you can see, right? This is very hard to scale, right? You have to hire maybe hundreds of thousands of humans operating these robots, so that you can get this training data, right? The same for auto driving. This is the reality. When you see a lot of auto driving vehicles on the roads, right, without any drivers, in the front, actually there are kind of people teleoperating those vehicles, maybe, right? They kind of actually drive the car remotely, so that they can get feedbacks. Right? So this is the traditional pipeline, right? It's very expensive, right? But with world model, right? Now you can use the world model to simulate, right, or given the possible consequences of actions. Naturally, you can use a world model to replace the real world, right? Use a world model to simulate different worlds, and then you deploy the agents in the simulated worlds and perform actions and observe the consequences. Use the consequences to run the reasoning agents, right? So here's a very simple example, right? Say we have a world model like this. This is a very domain-specific world model we mentioned that can simulate the in-house, the indoor household kind of situations. Okay. And then we deploy, say, large language models, right, as the reasoning agent, right, to do different tasks in this simulated world, right? Like say the language model, they may perform actions like grab pillow, give pillow to the other agents, blah blah, right? They can do a sequence of actions, and then they can observe the consequences by using the world model. Okay, and with this kind of action state type of data, you can create you can reformat the data into different forms, right? Like say here, you can have the training data for language models, right? Say if I take if I you can ask the language model, right? If I take this sequence of actions, what's the order of rooms where pillow appears? Where pillow appears. So because you have the simulated data, you know the ground truth answer, right? Simulated by the world model. So you have the answer. You can use this question answer pairs to train a model, right? So that's the kind of intuitions, right? With the simulator, right? The simulated environments using world model, you can get a lot of simulative experience for training, so that you get the enhanced reasoning agents, right? Enhanced language models, for example. Here are some of the results, right? So here, like for a small language model like GPT-J, right? This is for a small model like 60 billion parameters. By deploying these models in some of the world models, like these kind of indoor simulators, and train with this simulated experience or data, the model can outperform ChatGPT on many of the embodied tasks, right? Okay, and then yeah, you have the enhanced reasoning agent. In turn, you can deploy these stronger agents in the simulated world to collect better interactions, right? Because the model can do reasoning better, so it knows uh, uh, what are the more meaningful actions I should take in simulated worlds, so that you get more meaningful kind of feedbacks, right? So you get a more meaningful experience of training data to even train this agent itself in a better way. And you basically have this loop, right? You continuously get better data and train the model to get better reasoning capabilities. Okay. So yeah, that's kind of the other way of using world models to improve the reasoning, right? You can use world model to give feedbacks and training signals to train the language models or other reasoning agents. Okay. Yeah, any questions so far? If not, I'm gonna quickly mention some instances of world models, you know, of even broader scope of it. Okay. So now, okay, I want to even go beyond just a single agent, right? It's space and time simulation. I want to simulate many agents and their interactions. Okay. So that I can do this kind of social reasoning, for example. Right. Basically here, instead of just simulating this one particular agent or the physical environment, you also need to simulate, right? Maybe tens to like millions of other agents, right? How they interact with each other. So again, this is one particular instance we built. It's a kind of open-ended world simulation. We simulate humans, robots, vehicles, and traffic, social, financial systems in the simulator. We can simulate up to like 1,000 language model agents. So let's first watch the demo here. So you can simulate the kind of urban environment pretty realistically. And on the streets, there could be different agents. Okay. Each of the agents, they are intelligent, right? They have their own goals. They want to achieve their goals. Some agents, for example, they are delivering food, right? Some are maybe driving to their workplace. Okay. And then naturally they will interact with each other to achieve their own goals. Right. So in this simulated world, right, we simulate these different agents. They have different actions. You can simulate very diverse urban kind of things. Right, we can automatically generate the layout of the city and how different buildings should appear. It's an open-ended simulation. You can add all different elements into the world. And controlled by natural language. Like say, I want to add a building here. You get a building in simulated world. You simulate the traffic, right? And these vehicles they have to follow the traffic rule, right? Maybe, but of course there are some like rule breakers, right? So you need to simulate everything. And then with this simulation, you can do, for example, like how multiple agents they can collaborate with each other for food delivery, right? So here we simulate. Let me show this. Right here we simulate in this city, right? We simulate this maybe 10 different agents, right? And they are assigned the task of delivering maybe food to different customers, right? And we can simulate, okay, how this agent they should collaborate with each other, right? What's the best strategy for collaboration, right? To maximize the efficiency and or like minimize the cost of food delivery, right? So that's a very simple preliminary example, right? Once you can simulate multiple agents, right, their behaviors, you can use this to to find the optimal strategy, right? So collaboration strategy or like a social strategy, right, to solve different problems. Okay, yeah. The underlying engine is the Unreal Engine that people usually use to build like video games, right? And here we add an additional layer on top of Unreal Engine that you can plug in language models, right? Here, each of these agents here is controlled by a language model, right? So this language model, they can try to simulate um, the agent behaviors in a pretty realistic way, right? Like say this agent, you need to deliver this food from this restaurant to that customer, for example, right? So the agent they will do the planning, right, to decompose this task into a sequence of actions, right? So basically, yeah, each different agent they have their own goals, they have their own reasoning, right? And this simulator is to simulate, okay, how these different actions would lead to different consequences, right? And with this, you just roll out the simulation, right? And you can see, right? Say you have a objective, like to maximize the efficiency of food delivery. Then collectively, you can optimize for the best sequence of actions or different action they should take. Okay. Yeah, and naturally we see right many interesting behaviors emerge. Like say some agent they realize, okay, then I should collaborate with the other agent so that I can maximize the efficiency. Yeah. Yeah, so the text, we give a high level text instruction to a language model. Language model will decompose this into this function calls in Unreal Engine, right? So, and then, yeah, the simulator will simulate the effect. Okay. So this is another instance of world model as the multi-agency scope. So we can see, right, possible applications with this type of multi-agent simulation. Right, we can simulate human. We can do this human optimize human-robot collaboration. We can try to apply in public health, like say we can simulate how COVID-19 would spread, uh, across the city, right, by simulating all the different agents, their behaviors, and how this behavior would lead to spread of the of the virus, then we can try to optimize, like what's the best public health policy I should implement in this city, right, to contain the virus in the best way. Okay. The same for like economy or business, right? We can try to simulate the effect of different business policies to find the best one. And the same for education, for example, right? Okay, so yeah, these are the possible applications. Okay, maybe the last example of world models, because I'm running out of time, I believe. Yeah. Say I want to simulate the universe, right, or simulate maybe part of the universe, some laws of the nature, right, for scientific discovery. Okay. Somehow you can see, right, this first successful instance, right, AlphaFold. You can see that as a very domain-specific world model, right? It is doing this kind of protein structure prediction, right? Given a sequence of amino acids, right, what will be the 3D structure of this particular sequence, right? And with this, you can try to optimize, right? Say I want to have a protein like this, right? Then how I should design the sequence of the amino acid, right? So you can get the target structure of the protein, right? So this is a very simple example of a world model at this level. But people are now, right, trying to look at a broader scope, right? Can we build a world model, right, for like a single cell, right? This is the AI virtual cell project, right? If we can have a world model that can simulate all different activities in a single cell, then as we mentioned, right, you can use it for drug discovery, right? Because it can simulate. If I input this molecule, for example, into the cell, what will be the effect, right? So you can optimize the molecule, right, that can treat a particular disease, for example. Okay. This is something people are trying to do, right? They collect all these different heterogeneous biological data, like DNA, RNA, proteins. They have like for each of these modalities, right? They have 1D sequence, they have 2D structures, 3D structures, right? By collecting all this data, right? Hopefully, right, we can train a single model, right, that can understand all these different modalities, right, and simulate different activities, right. So literally, it's kind of virtual cell you can use to simulate activities of the cells. Okay. Yeah. So I'm gonna stop here. So some key takeaways from this talk, right? World models, we can build world model at different levels. Basically, more simulation you can do, the more intelligence you achieve, right? With a simulative reasoning type of paradigm. Right? And from the machine learning perspective, right, to really build these type of models, right, you need to have better models, better model architectures that can handle multi-modalities, right? Not just the natural language, but also videos, audios, and the DNA, RNA, right? There are different type of information. You need to have a better training algorithms, right? Say you need to train the model with simulated experience, not just the text data or video data. Those are kind of passive data you can collect, right? You need to actively interact with the world or interact with the simulated world to do learning. Okay. You need, after training the model, you need better inference algorithms, right? Using the simulation, right, to find the best plan for a particular problem, right? Then the challenges here is that how many possible future you need to simulate until you can find the optimal plan, right? That's very important for efficiency of the reasoning. Okay. Yeah, so that's it for today. I'm happy to take questions. Yeah.
So your city simulation, the model is telling physics engine that I want an object, and the physics engine is actually the one that's deciding how it interacts, right?
Yeah, that's a good question. So, in that example, it depends. Like I say, what the agent want to decide. Like you may decide, okay, give me a vehicle that is red. Then the model will give you a red vehicle. For other configurations, like how many wheels this vehicle will have, for example, right? This will be decided automatically by the engine. But you can give more complex instruction to control more things. Right. Yeah, exactly. Right. So that basically defines the generality of the engine. Right. The engine basically is the world model. Right. And what type of action it can take and simulate the effect of the action. Right. So again, the more actions you can handle, the more things it can support. Right. So yeah. Yeah. So first, world model from this perspective is not necessarily just a neural model, right? Like here in this world model agency is indeed a combination of neural models and the Unreal Engine, which is a traditional physics-based engine, right? So you can see whatever function that can predict next state, uh, given an action, you can see it as a world model, right? Again, and the scope of this prediction defines the general the utility of the world model, right? Um, so that's a clarification. And the second, yeah, so that's exactly yeah, maybe a small change in a particular step may lead to like a very different final effect, right? That's indeed again the idea of building world model, right? So the world model only need to take care of this one step simulation, and this simulative reasoning will take care of the complexity of the whole thing, right? You apply this step by for many iterations, you will arrive at very complex scenarios, and these very complex scenarios, uh, the final consequence may be triggered by just a single step, within this whole process, right? So that's indeed, the that's why we believe less feasible to really model these very complex worlds, right? Using by just modeling this the core world model, right? That's its next world prediction, right? Um, yeah, yeah. Um, Again, that depends, right? Depends on how you define the states, right? Say we show a couple example, like if you use language model as the world model, then yeah, you have to represent the state as text. But we also shown the pan world model that where the state is a video, right? Uh, So more precisely, we should say the action is text, right? And somehow, indeed, the model will first generate a latent representation of the state, the next state. And then we translate this latent representation into a video, right? So the video is the state, the action is the text.
Well, maybe you can questions during the break, because
Yeah.
we only have a 15-minute break, and then